In this video, we're going to talk about simplifying radicals. To simplify a radical, we need to use either the product rule or the quotient rule. So for square roots and cube roots or any kind of radical, we have the product rule, which allows us to separate or combine radicals over multiplication. This means that we can take any kind of root, a square root or cube root, an nth root, we'll say, and multiply it by another root of the same type. The index here must match, it must be the same type of root. Then we can combine that into one radical. And actually this rule works both ways, so we can either take two separate roots and combine them over multiplication, or we can take a root and break it up into two separate radicals that are multiplied. Likewise, for the quotient rule, we can divide two radicals, and if we like, we can combine them as long as they are the same type of radical into one giant radical where we divide the insides. And this one also works both ways. So if we have two parts and we want to combine them into one radical, we can do that. Or if we have one radical and we'd like to break it up into parts, we can do that, whatever fits the situation. Okay, so we want to make use of these to simplify square roots and cube roots. So to do that, we want to do a couple of steps. So the first step is to look for either perfect squares or perfect cubes. Obviously this would work best for square roots and cube roots. Those are going to be the majority of the questions we look at. If we were to move on to a fourth root or a fifth root, obviously we'd have to look for some different numbers. But we'll use these just to get the process going. Perfect squares would be a number like 1 times 1 is 1, so 1 would be a perfect square. 2 times 2 is 4, so that would be a perfect square. 3 times 3 is 9. Okay, maybe we can kind of go down the list together, right? The next one would be 16, 4 times 4, and then we'd have 25, 36, 49. We're up to 8 times 8, 64, 81, 100. I'm going to go up here. Okay, 11 times 11 would be 121. 12 times 12, 144. 169. Okay, those are all the ones I know. All right, so these would be numbers that would be good to identify if we were working with a square root. If we're working with a cube root, a perfect cube would be better to be able to identify. Perfect cube work the same way, except now we're going to multiply the same number by itself 3 times. So 1 times 1 times 1 would be 1. 2 times 2 times 2 would be 8. And we could also make a list of these. 27 would be the next one. 4 times 4 times 4 would be 64. 5 is going to give us 125. 6 times 6 times 6 would be 216. Okay, and we could go on from there if we really wanted to. So we want to identify either perfect squares or perfect cubes. Next, we want to use the product rule or the quotient rule to break up the root into parts, right? So we're going to take the square root or cube root that we have, we're We're going to break up the number inside into two pieces that are multiplied, one of which is a perfect square or a perfect cube, and then we're going to apply the root to the perfect square or the perfect cube to simplify. So let me give you a quick example. Let's say we wanted to do the square root of 40, right? So I want to break up 40 into two numbers that are multiplied, one of which being a perfect square. There are lots of ways to break up the number 40, right? If we really wanted to, we could make a list off to the side like we've done for some other things recently, right? 1 and 40, 2 and 20, 4 times 10, 5 times 8. Okay, I want to choose the pair where one of the numbers is a perfect square. And this is the only one that's going to work because 4 here would be a perfect square. None of these others are on the list, right? They're not a perfect square. Okay, so I can break up the square root of 40 as the square root of 4 times 10. The product rule says then I'm allowed to break that into two separate square roots, the square root of 4 and the square root of 10. And I know the square root of 4 is 2. So this becomes 2 times the square root of 10. Okay, so that's the basic idea for this section where we're practicing the skill of simplifying radicals. In other courses, it's usually more acceptable to write an answer in this form than it is to write it in this form. So this is kind of our chance to practice this skill because in other courses, if you go on from here to take other classes, this is not going to be an acceptable answer, right? The expectation is going to be for you to pull anything out of the square root that you can. And so now is our chance to try and master that. Okay, so there are some other criteria that we usually follow, and so I'll go ahead and add that in here. To be in the simplest form, a radical has all possible factors removed, so I pull out everything I possibly can to the outside by doing what we just did. Should have no fractions underneath the radical, and it's generally not accepted to have any radicals in the denominator. So we would want to move those out. Okay, so beyond that, I just wanted to try out a few examples with you, just to give you the basic idea. So we'll start with this one. Trying to get my papers in a good place. Okay, so let's try the square root of 75. Works the same way. We want to break up 75 into two numbers that are multiplied, one of which being a perfect square. I bet you could pick up right away that this is 25 times 3. Then using the product rule, I can break it up as the square root of 25 times the square root of 3. And I know the square root of 25 is 5. So I can turn that into 5 square root of 3. Let's see, we'll just do that. Okay, let's try another one. How about the square root of 72? This one's a little bit trickier, I think, because it's not a number that we are totally familiar with. There are lots of ways to break up 72, so I want to show you a couple of options because I think the most efficient option may not be the one we see first usually. Okay, 72 is 36 times 2. This would be the most efficient option. So if you came up with this, this would be the straight shot right to the end, okay? You have your calculator. You can use it to help you out as well, to test out different factors if you need to do that. I know the square root of 36 is 6. So I can write this as 6 square root of 2. Okay, let's say you did not see that. Let's say you were thinking 9 times 8. Okay, that'll work. The problem is that 9 is not the only perfect square hiding in this number, right? I could continue to break it down even more. So I could write the square root of 9 times the square root of 8, but I can also break up 8 into 4 times 2. Okay, and 4 is a perfect square. It's okay if you don't see the perfect square all in one shot. You can do it piece by piece. Anytime you bring anything out to the front, it gets multiplied with anything else that's on the outside. So the 3 and the 2 here are going to be multiplied. Notice we're going to get the same answer whether we do it all at once or we break it up into smaller pieces. It works both ways. Okay, what about the square root of 162? Maybe you don't know a lot about the square root of 162. Okay. Sometimes a factor tree works well. I'm trying to give you a lot of different options, tools that you can use, whichever you like the best. It's definitely divisible by 2. So if I divide it by 2, I get 81. And actually, 81 is a perfect square, right? I know the square root of 81 is 9. Okay, let's say that you didn't recognize that 81 was a perfect square. If you don't see a perfect square right away or you don't recognize it, you could use a factor tree to break your number all the way down into prime factors, numbers that I can't break up anymore. Okay, for a square root, remember we said at the very beginning of this chapter, the square root takes one of 2 equal factors. So for every 2 factors, I can bring one of those to the outside. So in this case, for every pair of 3s, 1 3 can come out to the front. Here's another pair, so another 3 can come out. The 2 does not have a pair, so he stays inside. Okay, notice I'm still going to get the same answer this time I did it in parts. Okay, so this is another option. Usually if I just don't see the perfect square right away, I can break it all the way down. Look at all the ends of these branches, and anything I can find that's a pair, whether it's next to each other or not, doesn't matter. For every 1 pair in the square root, 1 copy can come to the outside. Okay, for the cube root, we're going to do the same thing, but now we're going to look for perfect cubes. So can you think of how I can break up 16 into 2 numbers that are multiplied, one of them being a perfect cube? 8 is a perfect cube. So I could do 8 times 2. And then I can use the product rule again to break it up. I know the cube root of 8 is 2. So I get 2 times the cube root of 2. Okay, for 16, if we were to break 16 all the way down, let's just pretend we didn't see the 8 and the 2. Maybe we thought about 4 and 4 first. Each 4 breaks into 2 2s. When we're working with a cube root, any a cube root takes one of three equal factors. So any group of three can bring 1, 2 to the outside. And anything left over has to stay inside. So that same idea works here as well. Okay, what about, 532? Let's try this one. I don't remember how this works out, so this should be fun. Okay, let's divide it by 2. And you probably have a calculator. I don't have mine with me. Let's see. It's 266. Okay, and that's even. So that's divisible by 2. So 133. Is 133 divisible by anything? I have no idea. It's not divisible by 2 because it's not even. It's not divisible by 3. 4 is not going to work. 5 is not going to work. 6 is not going to work. 7 is going to work. Okay, 7. 7 goes into 13. One time, right? 63. Okay. Those are both prime, so I know I can't go any further. All right. Well, this is not a very good example because for a cube root, nothing can come out. I probably should have. I think I made a mistake on this one. Let's just pretend the cube is not there. How about that? Okay. Let's say it's a square root. Then for any pair, for a square root, because I adjusted it, right? One of 2 equal factors can come out. So the 2 can come out since we changed it to a square root, and I can't bring any of these out. Neither of them's a perfect square, so I kind of go back to here. Because anything inside the square root that's left inside will be left multiplied together. All right. Okay, so this has been a lot of examples that deal with just numbers. Now let's add in some variables. Okay, we'll start simple and kind of work our way up. So let's say we have the square root of 144, x squared. I can take the square root of 144, and I can take the square root of x squared. It's okay to think of them separately like that. This one I think we can all do very easily in our head. 144 is a perfect square. X squared is a perfect square. I think x times x. So we get 1x. Right? Lots of ways to think about these. Remember that the square root is also the same as an exponent of 1/2. So it's really going to cut in half any exponent on the variable. It's another way to think about it. Okay, what about this one? The square root of 48 x to the 4th y cubed. Let's start with 48. Lots of ways to break that up. If I wanted to break it up, and this is another one that might be helpful to use your calculator on. What is the biggest perfect square I could find? The biggest is if I divide it by 3, I'm going to get 16. That's going to be the biggest perfect square. Like we've said in the past, you could break it into smaller parts. You could break it all the way down. Okay, so if I take the square root of 16, a 4 is going to come to the outside. And I still have a 3 inside the square root. Okay, how about for x to the 4th? If I take the square root of x to the 4th, how many x's can come out? Think of cutting it in half if you want. Or think of there being 4 copies of x for each pair, because this is a square root. For every 2x, I can bring 1 out. I have 2 pairs, so 2x's can come out. Okay, for the y's, I don't have a perfect square here. It's not even, it's not going to go in evenly. You can think of it in two ways. You can think of dividing the exponent by 2 and using a remainder. Right? It's going to go in one time and have one remainder, and the remainder is going to stay inside the square root. Or you can draw out your 3 y's. Right? When I divide it by 2, it goes in one time. I get one pair, so one y can come out, and I'm left with one extra y that stays inside. Okay, let's do the same thing here. If I have the square root of x to the 17th, y to the 12th, how many x's can come out? How many pairs can I make out of 17? 17 divided by 2, I can make 8 pairs. 8 pairs would be 16, so I'm going to have one x left over. If you got really desperate, you could write out all your 17 x's and circle your pairs. I'm going to refrain from doing that, but if you got desperate, you could. 12 y's, how many pairs can I make? 6 pairs, so when I take the square root, I can cut the exponent in half. All right, how about a cube root? The cube root of negative 54. I want to do the same thing. I want to break it up in terms of multiplying, and I want to use the biggest perfect cube I can find. Again, use your calculator if you need to. This is even, so I would definitely start by dividing by 2 and see what I have. And when I do that, lo and behold, I get negative 27, which is a perfect cube. If I have a negative here, it would be really good to go ahead and take the cube root with that negative and pull it to the outside. So this is going to give me negative 3 from the cube root of negative 27 on the outside, and the 2 left over on the inside. How many x's can come out? For a cube root, I'm looking for groups of 3. So I have 3 x's, that's one group of 3. So one x can come out. When I do a cube root, it's like an exponent of 1/3. So I'm dividing the exponents by 3 now. How about for the y's? How many y's can come out? How many y's will be left inside? I have 5 y's. For a cube root, I have one group of 3, so one y can come out. 2 y's left inside. Okay, this is an idea that's going to take some practice, so don't be afraid to go in your book and look for practice problems. We're in section 7.3, so the exercises for that section are going to give you lots of practice problems if you're looking for those. Okay, I think I have a couple more. All of the examples we've done up to this point have used the product rule. So I thought I'd add in a couple that use the quotient rule. Remember, the quotient rule says if I have 2 square roots of the same type, I can combine them into 1. So let's do that. If I can combine this into one giant square root, 56x squared over 8. That works to my advantage because 56 is divisible by 8, so that gives me the square root of just 7x squared. 7 is prime. I can't break it up into anything with a perfect square, so really I can't do anything with the 7. It stays under the square root, but I can take the square root of x squared. So an x would come out, and the 7 would stay inside. Okay, so that's one use of the quotient rule. Let's do another one. Okay, this one is the same. Now it may be to our advantage to go ahead and reduce the 3 and the 12. Let's do that first. So 12 divided by 3, if I divide top and bottom by 3, I'm going to cancel out this 3 and leave me with x squared. I'm going to divide this by 3 so that I get 4y to the 4th left. Both the top and the bottom are perfect squares. So if it's easier to look at separately, the quotient rule allows you to do that. So you could take the square root of the top and the square root of the bottom. That's gonna give us x on the top. Square root of 4 is 2. The square root of y to the 4th would be y squared. And so that allows us to do that a little bit easier. Okay, well, I hope this has helped you get an idea of how to simplify a radical. I do want to encourage you to practice, and we'll see you in the next video. Thank you.